So let's first give a brief review of what we've seen so far in this class. So many of the problems we've considered involve supervised learning. So in supervised learning problems, the general task is to learn some function, capital F, that maps members of some set, capital X, this is a set of possible inputs, to members of some set Y, this is a set of possible outputs. So we're going to have some function, capital F, which maps some X to some Y. So, for example, in the parsing problem, each input X is a sentence, and each output is a parse tree. In machine translation, each input might be a sentence in one language, say French, and the output is a sentence in another language, say English, the language we're translating into. In part-of-speech tagging, the input is again a sentence, and the output is the sequence of tags, in particular the part-of-speech tags for that particular sentence, that sequence of words. So in supervised learning problems, we have assumed that we have some training set which consists of xi, yi pairs for I equals 1 to n. So for example, we would have n examples consisting of a sentence and a parse tree. Or we might have n translation examples, where each example consists of a French sentence paired with an English sentence. Or we might, in the tagging case, have n examples where each example consists of a sentence paired with a sequence of tags. And so we're going to somehow learn this mapping F from this training set. So we're going to have some algorithm that takes this training set as input and somehow produces some function, capital F, as the output. So almost all of the models we've seen so far are what I'll refer to as history-based models. So at a very high level, these models take the following approach. We break some structure, for example, a parse tree or tag sequence, into what you might call a derivation, or basically a sequence of decisions. So for example, we might have the sequence of tagging decisions, or the sequence of rule applications in a context-free grammar. I'll give some examples of this in a moment. Each decision has an associated conditional probability. So we might, for example, in the case of an HMM, we had conditional probabilities of the form ti given ti minus 2, ti minus 1, or e of xi given ti. The decisions here being to choose the ith tag given the previous two tags, or to generate the ith word given the ith tag. We multiply these decisions to get the probability of an entire structure. So the probability of a structure is a product of these decision probabilities. We typically estimate the parameters using variance and maximum likelihood estimation. So typically some kind of maximum likelihood estimation with some form of smoothing or regularization. And then finally, this function capital F, which maps input x to labels y, is defined as the label y that maximizes either the joint probability of x and y, think of HMMs or PCFGs as being one example of this case, or the conditional probability of y given x. This is what we saw with log linear taggers. So basically, we are going to use these history-based models to define either a joint distribution over inputs and outputs or a conditional distribution over outputs given inputs. But in all of these models, we've followed this methodology where we've broken structures down into sequences of decisions, associated each decision with a probability, and then multiplied these probabilities together to get the probability for an entire structure. Just briefly, here's a first example of this with PCFGs. So what is the sequence of decisions in a PCFG? We talked a lot about leftmost derivations or top-down derivations. So at each point in a derivation, we have some non-terminal, for example s, and our decision is to expand that with some rule, for example s goes to NP-VP. Each of these decisions has an associated conditional probability, so Q of S goes to NP-VP is a parameter that basically specifies the conditional probability of seeing the rule S goes to NP-VP, given that we're expanding S. The probability of a structure is a product of these terms. So if I have a rule with n rules, a tree with n rules, alpha I goes to beta I, for I equals 1 to n, then we just multiply together these Q parameters for each of the individual rules. Parameter values are usually estimated using variance and maximum likelihood estimation. In this case, this just means that our parameter estimate is the ratio of two counts, the number of times we've seen the rule, divided by the number of times we've seen the non-terminal alpha. And then finally, as I said on the last slide, the final function from a sentence to a parse tree is defined as follows. For any sentence X, we search over all possible parse trees Y and return the parse tree with the highest probability. The probability here being a joint probability over Y and X. Here's a second example, log linear taggers. So in this case, for a sentence of length n, we have n tagging decisions in left to right order. So for example, we might have the decisions determiner, noun, verb, if we had a sentence of length 3, for example. Each decision has an associated conditional probability. So this is going to be the probability of the ith tag, given the previous two tags, and given the entire sentence. The probability of a tag sequence conditioned on a word sequence is a product of terms where we have the probability of ti given the previous two tags and the entire word sequence. And in this case, we estimate or we define this model, this conditional model of the ith tag given the previous two tags in the sentence using a log linear model. And we saw how to define those models and how to define the parameter estimation method in those models. Finally, for an input x, we define the function capital F of x to be the y that maximizes the conditional probability of y given x.